Hello students, in this lecture we are going to be looking into alkenes. The previous lecture we finished up to alkanes. We saw synthesis, physical properties and chemical properties. The same we are going to see in alkenes, although in this particular video lecture I am going to be limiting myself to just the synthesis of alkenes. That by itself is a long chapter. This is taught in perspective of NEET and IIT JEE. Okay, some of the things that I teach here will come for you in 12th standard. If you are a 11th standard student, you will see some of them in the 12th standard during ether and alcohol. Okay, but I am teaching as though you have finished your 11th and 12th and you're preparing for NEET or JEE. Okay, this is in your syllabus, just when it is taught will be depending on your school. Okay, so in previous lecture when we looked into alkanes, we saw that alkanes are saturated hydrocarbon, meaning there are no double or triple bonds. Okay, here we have unsaturated hydrocarbons, unsaturated standing for presence of one or more double bonds or triple bonds. So if you have a double bond, you end with an ene, ene. Example here I have ethene. If you have a triple bond, you end with yne, alkyne. All right, so a common name for this is acetylene. We'll see in alkynes in the next lecture. When it comes to alkene, okay, few things we can see. When you look at a double bond, okay, this particular carbon here, it has sigma bond here, sigma bond here, and sigma bond here. There's a pi bond, so it has 3 sigma bonds, so it will be sp2 hybridized. This is also a sp2 hybridized carbon, whereas the carbon here has 1 sigma and 2 sigma, and this is a pi bond, this is a pi bond, so 2 sigma bonds leads to a sp hybridization, right? Okay, that's something you need to know. Second thing you want to know, sp2 hybridization, meaning the carbon is attached to 3 different entities. Okay, here we don't have a lone pair, so 3 different entities, so the ideal bond angle is 120 degrees. Okay, so this bond angle right here in an alkene is close to 120 degrees, although it is not exactly 120 because these 3 atoms are not similar. Okay, exactly, is it going to be greater than or less than 120? You can see in chemical bonding, at least here for now this is more than enough. This particular carbon has a trigonal planar geometry around it. Okay, trigonal planar, so all of the carbon, hydrogen and this hydrogen is in one plane. So this particular molecule ethene, all the atoms are in one particular plane. Okay, ethine is not only planar, it's also linear, it's in one straight line, a linear compound. Okay, now here you don't have to remember these values, but just kind of crudely know the order of the length of the bond. So once the bond becomes multiple order, a single bond goes to a double or to a triple bond, the atoms come closer or the bond length shrinks. So a single carbon-carbon bond is longer than a carbon-carbon double bond, which is longer than a carbon-carbon triple bond, and anything in between. Okay, for example, if you take benzene would come right in between, because if it were this way, this should have a length of carbon-carbon double bond and this should have a length of carbon-carbon single bond, but benzene is actually a resonance hybrid of this structure and this structure, so together they will give you 1.5 bond order. Okay, so this is going to be between these two. We are going to see benzene and aromatic hydrocarbons separately, but at least know crudely the values. Just remember 1.5 and 1.3, and this is going to be less than 1.3, or you can even remember 1.2. Don't try to memorize, you see it a couple of times, you will start remembering things. Okay, so benzene is going to be somewhere in between, roughly 1.4 if you want to remember. Okay, 1.5 bond order. Okay, this is straightforward bond order. How a single bond is longer than a double bond, which is longer than a triple bond. Okay, once the bonds are stronger, okay, they become shorter. So if I were to arrange them in the order of length, bond length would be this order. Okay, this is bond length. Bond strength would be this order. Okay, this is stronger to break all the three bonds in general. Okay, but if the question is asking you very clearly how much energy is needed to break the carbon-carbon bond in ethane compared to ethylene compared to acetylene, obviously the bond strength is higher here, so this is going to have the highest amount of energy I need to input. But if they're talking about breaking only one bond, we are talking about breaking a sigma bond. Here I am going to break only one bond, so one of the bonds, pi bond. Here I have three bonds, I am going to talk about only one of the bond, meaning pi bond. So if you compare the energy to break just a single bond between the carbon-carbon here, so this will be the highest. Next, this is the highest because I'm breaking a sigma bond, whereas in these two cases I'm breaking a pi bond. So again, two different scenarios. One is breaking all the bonds altogether, meaning this is going to be tougher because I have to break three bonds. Okay, but if I'm talking about only breaking only one bond, okay, obviously this is higher. If it makes it easier for you, I can put it this way. Let's say for example CC bond energy is X. Okay, C double bond C is not 2x, it's going to be less than 2x, it doesn't double. Okay, C triple bond C is not 3x, it's much less than 3x. Okay, alright. So if to break three bonds I have less than 3x, to break one bond I will have less than x. Remember that way. X way. No, I need x for this one, this is less than x. So it is easier to break one bond from here. Again, these are properties where in JEE and NEET they ask you, it doesn't come really under unsaturated hydrocarbon, it comes as organic chemistry in general. Okay. There's one more table I want to show you. How presence of a double bond alters the length of a CC single bond. See, here we compared single versus double versus triple. Here I am comparing CC single bonds. So I am basically comparing this bond versus this bond versus this bond versus this bond. Okay. Although they are all CC bonds, carbon-carbon single bond, they are different in terms of their vicinity, where they are present. Their neighbors are different. Here it's all hydrogen. So this is 1.5 angstroms, just like here, 1.54 angstroms, just like here. But when I put a double bond to one side, okay, this is sp2 hybridized, this is sp2 hybridized, electronegative, greedy. Okay, so this bond shrinks, so it's less than that. When I put it on both sides, okay, it shrinks even more. So look at the length goes down, the bond length is shorter. Okay, similarly when on one side instead of a double bond I put a triple bond, okay, the length shrinks even more than even two double bonds on either side. So having a single bond carbon carbon doesn't always mean 1.54, it depends on the vicinity. If I have unsaturation or electronegative element here, the bond length here shrinks. You can look at it this way. This is electronegative, okay, this is electronegative, it pulls electron, so this one pulls electron, this brings shorter, so the bond length becomes shorter. Okay, all right, let's look into basic IUPAC of unsaturated hydrocarbon, just simple ones. So when you look into IUPAC, you want to look at the principal functional group. I told you guys already, you have to look into CBSE book for the order of the functional groups. Carboxylic acid is the first, then SO3H, so on and so forth. So when you look at the order here, your alkyl groups and halide groups always come towards the last. Okay, before them comes the double bond, before them comes the OH. So OH is the priority here. Okay, so this is the priority, so this becomes automatically carbon 1, this is carbon 2, carbon 3, carbon 4. So IUPAC of this would be 1 2 3 4 bute. In carbon 2 and carbon 3 I have a double bond, so it's enough to say it is carbon 2. It means the double bond is between 2 and 3, 2 in 1 all, because there is carbon 1, there is, I have 1 all. Okay, bute 2 enol, it's not the correct way of saying, but still it is understood. If I say 2 enol, it means the all is in one carbon, but it is better to say it this way. Okay, now when I go to this compound, I have a double and triple bond. Okay, So normally a double bond is more priority compared to a triple bond. Okay, but it also depends on numbering. 1 2 3 4 5, 1 2 3 4 5. So when I look here on the top, I will have pent, okay, 3 in, sorry, 2 in, 2 in, 4 in. So when I go this way, okay, I will have pent 3 in, 1 ion. So 2 plus 4 is 6, 3 plus 1 is 4, or I get 1 for the priority. So lowest numbering I get here. So this is the correct IUPAC, not this one. So again, if double and triple are present in the same numbering, okay, then double bond wins. For example, same compound, I have a triple bond here, I have a double bond here. So if I go this way, double bond gets priority 1. If I go this way, triple bond gets priority 1. So my double bond wins. But they are in unequal positions, so you go with the numbering. Okay. And also when you say the way you want to say, once I know that it's 3 in and 1 ion, I always say my in before ion because E before Y. So it is not going to be pent 1 ion 3 in, it is going to be pent 3 in 1 ion. Okay. Now going to these compounds. So you want to make sure that you do the lowest numbering rule for the double bond. So obviously this is the ring. Okay. So I can either call this one as carbon 1 or this one as carbon 1. There is no merit to call this as carbon 1. Okay. Apply the carbon 2, I will get 2 methyl. Instead I can get 1 methyl. Okay. So this is what we are going to do. If you look at it, here I have, this is carbon 1, carbon 2, carbon 3, carbon 4. So it becomes 1 methyl, 1 comma 2, there is ene, so 1 ene, okay, and then cyclohexane. So I have the cyclohexene. I don't have to say 1 ene, it is understood, cyclohexene. In position 1 I have methyl group, and position 4 I have isopropyl group. Okay. Now why do I do the isopropyl writing down before methyl? Because this is I before M. Okay, iso is IUPAC, so you compare the I here compared to M. Going to this compound, so I have this as a substituent. I have 1 2 3 4 carbon as the longest chain, so I give my number, sorry, 1 2 3 4 as the longest chain. So I take this as my longest chain. Okay, 1 2 3 4. At position 1 I have cyclobutyl. Position 3 I have methyl. So 1 cyclobutyl, 3 methyl, 1 butene. So 1 butene. So when I take this one, if you just count the number of carbons, doesn't matter where you start, let's just first count the number of carbons. Let's take double and triple. I told you double gets the preference, so I start with 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's going to be, okay, 10 carbons, that is going to be decane. Okay, but this is going to be a cyclo, so it's going to be cyclodecane. I have 1 ene and 4 ion. So hence what we can do, cyclodecyne, but my position 1 I have a double bond, so 1 cyclodecene, 4 ion. It can also be written as cyclodec 1 ene, sorry, hyphen here, 1 ene, 4 ion. Last one. So if you see, there is 8-membered ring. So 8-membered ring means you are going to have cyclooctane, but this is going to be triene, so I have to number them. So I told you the halides get the last numbering, so I have to go with this one. This particular group is called vinyl. C double bond C is vinyl. So we saw allyl and vinyl before in organic effects. So this is vinyl. So I give the lowest numbering. So if you start naming from here 1, 2, 3, 4, 5, 6. If you go this way and if you go this way, write down both of them. You will see the lowest locant rule. This is the best way to do. 1, 2. So I have a 2 position vinyl. At 5 I have chloro. I have 2 of them. So you have to say 5 comma 5, saying both the chloro are in the same carbon. 5 comma 5 dichloro, 2 vinyl, 136 cyclooctatriene, or you can also say cyclooct 1 comma 3 comma 6 triene. Okay, going to a double bond equivalent or degree of unsaturation. Okay, what it means is basically when I give you a formula, you can figure out whether there are double bonds or not. Okay. If I give you a molecular formula and I ask you to write down isomers, we saw isomerism before. If I ask you isomers, you need to know whether there is unsaturation or not. So this is a crude formula you can use. C stands for the number of carbon atoms. Okay, if there is C4, H8 something, so C means 4. So this is number of carbon atoms plus 1 minus number of hydrogen atoms by 2 minus number of halogen atoms by 2 plus number of nitrogen atom by 2. So there is a reason why you go with this. 2 hydrogens give you, loss of 2 hydrogen gives you 1 double bond. So minus means loss of 2 hydrogens, okay, is 1 double bond. Okay, 2 hydrogen is 1 double bond, 1 hydrogen is half a double bond, so H by 2. Similarly, loss of 2 halogen is this. Nitrogen, you do a plus because nitrogen is capable of forming 3 bonds. So if you look into this formula, you can actually calculate it. At this point, we'll just take this as the formula. Okay. Now we'll do both ways. Given structure, we'll figure out whether double bond equivalent works, and also we'll look into a formula and see whether we can write down the structure. So this is benzene. What all do we know about benzene is it is C6H6. Double bond equivalent equals the number of carbon is 6 plus 1 minus number of hydrogen is 6 by 2. Okay, so that is going to be 7 minus 3, that's 4. Okay, so what it means is 4 degree of unsaturation or double bond equivalent. So it is not always going to be a double bond, it's equivalent to a double bond. What all is equivalent to a double bond? 2 double bonds is equal to a triple bond because pi and pi gives you 2 pi. A ring is equal to a double bond. Okay, so now if I have 4, I can have 4 double bonds, okay, or I can have 2 triple bonds, or 1 triple bond and 2 double bonds. So any of these structures possible. Okay, so now if you see benzene, so that's 1 double bond, another double bond, another double bond. So I have 3 pi bonds plus 1 ring, so that is 4. So degree of unsaturation is 4. Now let's take a couple of examples here. Now these are very good example. If you see this one, anytime you have a ring, that is 1 degree of unsaturation. So I see 1, 2, 3, 4 double bonds plus 2 ring, so that is going to be 6 degree of unsaturation. So here 1, 2, 3, 4, 5 plus 2 ring is 7. Here I have 1, 2, 3, 4, 5. Okay, so I have 5 plus 2 ring is 7. Okay. Now if I want to calculate it through this formula, okay, they give you this formula. I need to know double bond equivalent without knowing the structure. What we would do is, using this, we can write number of carbon is 11 plus 1 minus number of hydrogen is 11, okay, plus number of nitrogen is 1. Okay, so this is going to be, if you look at it, this is going to be 12. That equals 12 minus 11 by 2 minus 11 by 2 plus half is going to be minus 10 by 2, which is 12 minus 5 is 7. That tells you the double bond equivalent is 7. At least it will tell you that. Okay. Now if you see, if you count the carbons and the number of double bonds, number of cycles, you will see that it matches. Now how can this be useful in NEET and IIT? Okay, this is for you to understand, reverse calculate. But in NEET and IIT, we can have the other way of problem. They can give you the structure and ask you double bond equivalent, which is rare. They would more likely give you the formula, ask you how many isomers. Let's take this example. It's a very good example, very small one. They always give you a small one so that there is not a lot of isomers to write. So the double bond equivalent is going to be number of carbon, which is 4, plus 1 minus number of hydrogens by 2. That's 5. Okay, minus 4 equals 1. So I am having one double bond equivalent. So that can be one double bond or one ring. Now C4H8, what all can we do? Carbon, 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 carbon. I have a double bond. So I can have a double bond here. That's one structure. That's another structure. Okay. Now we don't have to stop with this. We can do, these two are positional isomers. Okay. This and this are chain isomers. Now we have done this. Now is there any other way that you can arrange a double bond? If you put a double bond here, it's still the same molecule. If you put a double bond here, it's still the same molecule. So these are the three unsaturated compounds that you can write. Okay, but there is one ring possible, so I can also write 4 carbons this way. This is a saturated compound, this is unsaturated compound, but we can also draw a smaller ring. Okay, so these are the isomers possible. So if they ask you how many isomers are possible, all these are possible. Okay, if they ask you how many isomers will answer bromine water test, meaning double bond has to be present, 3 of them will do. Okay, how many isomers have a double bond means only 3 of them will do. How many saturated isomers means only 2 of them will be. Okay. Hence double bond equivalent is useful to figure out saturation or unsaturation, and based on that I can figure out my cyclic and non-cyclic. If plainly people give you this, what I have seen is people always miss the cyclic isomer. But if you go through the double bond equivalent route, the next thinking after you calculate this is going to be ring or cycle. Okay, after the double bond, it's going to be a ring or a cycle you're going to think. So you won't likely miss these isomers. Okay, now here just for you to know the unsaturated compound alone, I have also given you numbering and naming. This is for you to look into it. Okay. Now there's another question, just to reiterate it. Two hydrocarbons have the same molecular formula. Hydrocarbon A decolorizes bromine water, but B does not. Explain the observation. So if you were to look into double bond equivalent, it is going to be 5 carbon plus 1 minus hydrogen by 2. That's going to be 6. Correct? Okay, minus 5 equals 1. So I have 1 degree of unsaturation. Carbon A decolorizes bromine water, meaning hydrocarbon A has a double bond, but hydrocarbon B does not, meaning it's a cyclic structure. Okay, now A can be any of the isomer that has a double bond. B can be any of the isomer that has a cycle. For example, if you were to draw a compound with 5 carbon atoms and a cycle, I can start with 3-member cycle, 4-member cycle, and 5-member cycle. Now I need to have 5 carbons, so this is good. There's only 4, so I need to have 5th carbon here. That's good. When I take this one, okay, this is one isomer, this is another isomer possible. Okay, now this helps me in drawing all the possible isomers, double bond equivalent. Right, now hydrocarbon A must be unsaturated, but hydrocarbon B must be saturated, so it could be cyclopentane. Could be, not always, could be. Only these are also possible. Alright, so let's look into the nature of the C double bond C. It's basically between 2 carbon atoms. So they have a sigma bond between them. A sigma orbitals of carbon and sigma orbital of carbon, they combine and give you a sigma bond between them. And there are 2 p atomic orbitals. So this is the atomic orbital, p orbital of a carbon. This is p orbital of a carbon. Okay. They cannot overlap head on because already it is overlap. So these are perpendicular to this axis. Remember that these two lobes make up one p orbital. It's a dumbbell shape. Okay, this is also a dumbbell shape. They can overlap sideways. Okay, what it means is they can overlap this way with each other. Okay, if they overlap sideways, here you can see that they can overlap sideways, and then they can form a two p orbitals, give you one pi molecular orbital. Okay, a pi cloud above and pi cloud below. These two still make up two lobes which make up only one pi orbital. Okay, now the orbitals join the two atoms so that they can no longer spin. What it means is this is a single bond. Once this double bond is formed, okay, these carbons cannot spin individually, independently, giving rise to geometrical isomer, cis-trans isomer because of this. Okay, this is again a different schematic of the same. If I have just shown you in three-dimensional. Okay, so carbon-carbon single bond, sigma bond is formed. Look at this carbon, a sigma bond is here, sigma bond is here, sigma bond is here. So it has formed a sigma here, a sigma here, and a sigma here. Okay, so this carbon and the carbon next, they both are sp2 hybridized. Okay, the p bonds or p orbitals overlap sideways to give you pi orbital, but the pi orbital or the pi bond do not take part in hybridization. Only the sigma bonds and lone pair. We have seen this in chemical bonding. So I still have sigma, sigma and sigma. No lone pair. So 3 sigma bonds give rise to sp2. Okay. S1, P2, 1 plus 2 is 3. 3 sigma bonds. Okay. And this gives rise to two things. One is bond order has gone up compared to a single bond. Bond strength has gone up. Okay, if you want, you can also write bond length has gone down. Okay. Now that we have seen the basis of alkenes, let's go into synthesis of alkenes. Okay. Here I have done synthesis on the perspective of NEET and IIT JEE. Okay, little bit more in detail. It's still in your syllabus, but some of them will come for you in 12th standard syllabus. So if you are a 11th standard student, okay, you can skip the mechanism part of this individual synthesis, but if you study the mechanism, it makes it easier for you. Okay. First we have synthesis of alkenes from alkynes, a triple bond going to a double bond. Okay, so it is going to be partial hydrogenation. Complete hydrogenation is Sabatier-Sandrens reaction. You can use H2 with nickel or palladium or platinum or Raney nickel catalyst. Rhodium and ruthenium will also do, but that is complete hydrogenation. This is partial hydrogenation. And there are two syntheses. The first one is Lindlar catalyst. It's a heterogeneous catalyst. Heterogeneous catalyst meaning it's two different medium. Okay, hydrogen is gas and the catalyst is going to be solid, so it is not the same phase. So heterogeneous catalyst that consists of palladium. If I were to do only palladium, okay, an alkyne will give you alkane. So I have to slow down the reaction first of all. So I deposit the palladium on calcium carbonate or barium carbonate. So what happens is the palladium surface area is covered because they get attached means the side that it is attached surface area is less, so it becomes slower. But just because you decrease the surface area doesn't mean it will stop with an alkene, it will go to alkane eventually. So what I do is once I cover the surface area, I also make sure it stops with alkene, so I poison the catalyst. Poison means losing its complete activity. Okay. So what happens is when I poison it with either lead, sulfur or quinoline, any of them, okay, a triple bond gets converted only to a double bond, doesn't go to a single bond. Okay. In NEET, sometimes they just give you calcium carbonate or barium carbonate, they don't give you the poison, but it's still assumed that it is a Lindlar catalyst. But in reality, these will slow down the reaction, but you want poison itself. Now this is very similar to a reaction that you will see in 12th standard. If you are 12th standard students or a repeater, you would have already seen. Rosenman reduction is exactly same. it's still partial hydrogenation. Okay, you have an acid chloride giving you aldehyde, doesn't go to alcohol, not a complete hydrogenation. Okay, so now if you see here, an alkyne giving you alkene, an alkane giving you alkene. All right. Now this is a syn addition. Syn means same side addition. So you see the hydrogens, they are attached to the catalyst surface. I've shown you this diagram in Sabatier-Sundrum's reaction in alkane synthesis. Hydrogens attached. It goes and attaches on the same side to the alkyne. Because it attaches to the same side, the R group, both of them go to the same side. So they give you cis alkene always. Okay. So it's syn addition giving you cis alkene. Here is an example. So here we have a triple bond, okay, ending up with a double bond, but I get the cis isomer, I don't get the trans isomer. Okay. Here I have the next synthesis. It's exactly similar, an alkyne going into an alkene, partial reduction. The catalyst is different, it's called Birch reduction. Technically Birch reduction is completely different. Okay, an aromatic compound becomes a cyclodiene, but this is also possible to convert an alkyne to alkene. What you use is, you use dissolving metal reduction. You will see this particular one in your S block as well. When you study group 1 about properties of S block, when you take a S block element, okay, like sodium, you take sodium and put it in ammonia, okay, it is soluble in ammonia, but it actually loses a electron, and the electron is solvated by ammonia. This is a solvated electron. Okay, it actually gives you a blue color in this particular case. Okay, the solvated electron, this electron will go attached or attack a triple bond. Right, so now this electron will go attack a triple bond, so giving rise to, okay, a carbanion. You don't have the mechanism in your syllabus. Anyways, now that you have a carbanion, if you have this, can donate the electron to form a bond with the hydrogen donor, acidic hydrogen donor. So always this is missed, but this is invariably always present. Very little of alcohol is present to give you the hydrogen. Just sodium and liquid ammonia. Okay, this ammonia doesn't give you the hydrogen. It's always from a hydrogen donor like an alcohol. This gets attached and you get the corresponding alkyne. So previous slide we saw Lindlar catalyst. It was a syn addition giving you cis compound. Birch reduction is anti. Syn is same side addition, anti is opposite side addition. It gives you trans compound. So these two reactions are complementary. One gives you cis if I want cis, one gives you trans if I want trans. Complementary reactions are extremely important. Okay? Depending on the product you want, you can choose the corresponding catalyst. Okay, let's look into this one. What are the products in the given reactions? So when you take first one, this is going to be Lindlar catalyst. So I'm going to have, this is a carbon and a carbon. So I'm going to have a carbon-carbon double bond attached to 5-membered ring, and the hydrogen goes here, 2 carbons. So this is syn addition. So this is going to be cis compound. This is Birch reduction. This will be the corresponding trans compound. So hydrogen over here, right? How can we name this? So when you take this one, you see that 1, 2, okay, this carbon, sorry, 1, 2, 3, 4. So this is but 1-ene, 1, 2, 3, 4. This is 1, 2, 3, 4. But 1-ene. In position 1, I have a cyclopentyl substitution. So this is 1 cyclopentyl, but 1-ene. This compound is trans. This would be cis 1 cyclopentyl, but 1-ene. This reaction is no particular Lindlar catalyst or Birch reduction. So this is going to be Sabatier-Sandrens reaction, complete hydrogenation. So I will have carbon, single bond carbon. Okay, sorry if I remembered. Okay, okay, that's good enough for us. Okay, so this will become a single bond. So this would be 1, 2, 3, 4, 5 pentane. Okay, this is cyclopentane. So you can say pentyl cyclopentane. I know that it sounds weird. So here a cyclopentane becomes the ring, main ring, and here you have C5. So this is pentyl group. Okay, pentyl cyclopentane. You don't have to say because the numbering automatically is 1 pentyl cyclopentane. As I said, organic chemistry, you cannot memorize the reactions. The best way to do it is practice problems. Hence, I'm putting problems in between the slides. Okay, so now we saw how to get alkene from alkyne. The next we are going to see, this comes predominantly in NEET and JE. A lot of times, synthesis of an alkene by dehydrohalogenation of alkyl halide. Okay, alkyl halide. Here you see that this is an alkyl halide. This X and this H goes away in presence of a base, and this is called a beta elimination. So in conventional organic chemistry, the carbon that is attached to the halogen is called alpha and the neighboring carbon is beta. So if we lose a hydrogen from the beta and the electrons come over here, this goes out with the electron, hence it's called beta elimination. Okay, this is also called 1,2 elimination. There is a modification of this 1,4 elimination. We are not going to see that now. This is 1,2 elimination or beta elimination in presence of a base. This base has to be an alcoholic base to get elimination product. The reason because if it's not an alcoholic base, you will have substitution reaction as well. Okay, remember bases are also nucleophiles. It can replace X as a leaving group and the nucleophile base can attack as a nucleophile and become substituted here. So hence you want an alcoholic medium where it doesn't behave like a nucleophile, it behaves as a base. You want to remember these orders are asked. They don't ask you to write down the order. They give you 4 different molecules and ask you which one reacts faster or which one reacts slower. Okay, and iodide, obviously this bond is longer. So this is carbon, this is halogen. Let's say this is chlorine, this is bromine, this is iodine. So this iodine bond is longer, so it breaks easier. Iodide, carbon iodine bond is not as strong as carbon chlorine bond. Okay. So an iodide will react faster. Similarly, a 3 degree carbon will eliminate faster than a 2 degree compared to a 1 degree. This is because of steric reason. A 3 degree carbon is very crowded, so it wants to get rid of the crowded problem by eliminating. So you want to remember both of them. Don't remember it just by memorization, understand why. It's easier that way. Okay. Here I given you the mechanism, E2 mechanism, meaning elimination bimolecular. We have already seen the types of reaction, elimination, E1, E2, S11, SN2. So if you look there, E2 mechanism is when the rate of a reaction is equal to rate constant times the base and the substrate. So here both the base and the substrate take part in the slowest step or the rate determining step. You want to remember that dehydrohalogenation is E2 mechanism. Okay. It happens in one homogeneous step. The base abstract a proton, this electron moves over here and the leaving group goes away, forming a double bond. So it doesn't happen in 2 steps, it happens in 1 step. Okay. So here there's another example. Most of the time you will see in NEET you get cyclic compound. Cyclic compound, if you just ignore looking at it, just focus on this, it doesn't look like cyclic, it's just point of focus right here. So don't get scared of cyclic compounds. With enough practice you will be alright. So base attacks a hydrogen, the electron moves over here giving you a double bond, chlorine goes away. This hydrogen is beta hydrogen. This is going to be acidic because this is minus I group, electron will be pulled. So this carbon is electronegative, making electron being pulled from this carbon. This is a little electronegative. So this hydrogen attached to electronegative carbon is basic. So hence it's easy for the base to abstract this hydrogen compared to any other hydrogen over here. Okay. Now there is also alpha elimination. Okay, just a brief introduction. Alpha elimination. Let's say for example CHCl3. You put the same base. You get Cl, Cl, Cl minus. Okay. The OH minus has taken the hydrogen leaving the electron. Now what can happen? This chlorine can leave and give you CCl2 dot plus Cl minus, leaving this electron. So this goes away. So CCl2 electron. This is dichlorocarbene, the intermediate in Riemann-Tiemens reaction. Okay, and this carbon has 2 sigma bond and 1 lone pair. So sp2 hybridized, 1 2 and 2 sigma bonds, meaning 2 bonds here. So 1 2 3 4 5 6 electron around it. So a carbene is Lewis acid. Okay, now because I have lost the electron from the same carbon, alpha carbon itself, okay, I have lost this hydrogen. Here I lost the hydrogen from the beta carbon, beta elimination. Here I have lost the hydrogen from alpha carbon, so it is alpha elimination. Okay. So if alpha elimination is tough for you, just ignore this one. Focus on the beta. Make sure that you understand this. Dehydrohalogenation is going to give you a double bond. It is going to be a single step process. E2 mechanism depends on concentration of base as well. Okay. Now what type of alkene can be formed? This is extremely important for NEET and JEE. Okay. Zaitsev, you see that there are many ways of saying the name. Is named after the Russian chemist who actually figured out that when you do an elimination reaction, the alkene that is formed is going to be the most substituted, and that will be the major product. Okay. Remember, we already saw hyperconjugation. The more the substituted an alkene is, the more the number of hyperconjugated structures. So obviously that will be the most stable product, meaning major product. So Zaitsev role is nothing but the product that is going to have a lot more hyperconjugated structures. Okay. So generally in elimination, when you do this, you're going to get major product, the most substituted alkene. What type of bases will give you? Strong, less hindered bases generally will give you Zaitsev product. Henceforth, we are going to say it as Zp as major. So here is an example. So now when you see this example, this is the alpha carbon. So this is beta, this is beta. So I can have a double bond here. Okay, maybe this way. I can have a double bond here, this. Both are possible. The OH minus here is capable of attacking and taking the hydrogen from both of them. Okay, but this is going to be a major product because if you look at this double bond, it has 3 alpha hydrogens here, 3 here and 3 here. Whereas if you look at this double bond, okay, there's no alpha hydrogens on this side. Okay, this is 3 here and 3 here. Okay, now here when I say alpha, it's relative to the double bond. The next carbon is alpha. Here when I say alpha, okay, the carbon attached to chlorine itself becomes alpha. These are conventions. Don't confuse that. Here I'm saying this is alpha, not the next one. Okay, so here 6 hyperconjugated structures, here 9. So I will get the most substituted product, that is going to be a Zaitsev product. The one that is less substituted is called Hofmann product. We will see in the next slide, HP. Okay, here when you see it says H2O, normally you need heat because it's not alcoholic. But if it is alcoholic, okay, it will easily give you elimination. We will see the role of alcohol pretty soon. Okay, one more example. When you see here, so this, if you take it as alpha carbon, that's beta here, this is beta, but these two are exactly same, so it doesn't really matter. This is a beta carbon. Okay, so I have carbon 1 and carbon 2. So if I remove from carbon 1 hydrogen, I'll end up with this. From here I'll end up with this. This is a more substituted alkene. If you want me to write down, there is 3 alpha hydrogens, 2 alpha hydrogens and 2 alpha hydrogens, whereas when I take here I have 2 alpha and 2 alpha. Obviously this is more stable, more substituted alkene. Tri-substituted means there is, for this double bond there is one substitution here, one substitution here and one here. This is not a substitution, this is just hydrogen. So this is going to be 80%, this is going to be 20%. This will come straightforward in NEET. They can give you this and then they can ask you what is going to be the product, or it could be very well be A gives you B, they'll give you what this is, B gives you C. You know that B is going to be an alkene because you saw this one. Okay, next, stereochemistry of elimination. This is not that often asked in chemistry in NEET, but it's still in your syllabus. Every couple of years you can expect this one. So when you look at this compound, so we have beta carbon here, beta carbon here. Okay, so I can have either a double bond here or a double bond here. We have figured out that this double bond is more stable. Okay, compared to this double bond. So this is going to be a minor product. So we are not going to worry about it. Among the butene that you see, trans butene is more stable than cis butene. Okay, by stereochemistry this is less hindered than cis butene. So trans is going to be more stable than cis. Okay, remember we already saw heat of hydrogenation. Trans is going to be more stable than cis. So this is a major product, this is a minor product. There is always a competition of elimination versus substitution. Okay, this is substitution. This OET minus can take away the hydrogen. If it takes away the hydrogen, it behaves as a base. Behaves as a base, you get this compound. But it could also behave as a nucleophile. If it behaves as a nucleophile, it replaces a leaving group. Okay, it replaces Br and gives you this. Okay, this is E2 mechanism. But when it behaves as a nucleophile, okay, it can go SN1 or SN2 if it undergoes SN2. Okay, meaning inversion of configuration, which we already saw before. SN2 leads to inversion, whereas SN1 leads to racemic mixture. This will undergo both SN1 and SN2. If it is 3 degree, predominantly SN1. If it's 1 degree, it will be predominantly be SN2. Okay, this is an interesting problem. This is a little bit, it's not high in level, but it has got to be a question where attention to detail is important. Now, if you look at this, the expected product should be a double bond here because it is the more substituted alkene. So you should have expected this compound, correct? Should have expected this more substituted, but this is the only product. You don't get this because this is the E2 mechanism and it is an anti-elimination. The hydrogen has to be anti to the bromine, meaning if the bromine is shown this way, the alpha hydrogen, and the beta hydrogen has to be this way. But here if you see in the beta carbon, the one facing away from bromine is this methyl group. The hydrogen is towards you, not shown but towards you. So it's impossible. Here when you see, I have two hydrogens, one is away, one is towards you. So this hydrogen and this bromine are more likely to go. This is impossible. So you don't get a double bond here, you get a double bond here. Okay, so this is a little bit higher in level. If I don't give you stereochemistry, if I just give you this, you are free to take that this bromine and this hydrogen that is not shown here are anti to each other and give you this as a product. But if I decide that this is how they are going to be, you have to know. Very simple. How do you make in the exam? Make yourself think about it. Right away if you see this, stereochemistry should come into your mind. Okay, your first step should be, alright, this is my alpha carbon, identify my beta carbons and draw the remaining ones. And make sure if you want, draw big. easier. Hydrogen, here hydrogen. So this is towards you. I'm seeking for something hydrogen away from me, not present. So a double bond here. That's your compound. Again, you don't have to draw separately. Finish it off in what's already printed. Alright, let's do a quick exercise. As I told you again, organic chemistry, unlike your other parts where you learn the theory and do the problems, organic, you learn a little bit of theory, do the problem and get stronger. So this is alcoholic KOH. Okay, this is alcoholic KOH. If it's not alcoholic, if it's aqueous KOH, OH minus will replace Br. Okay, but this is alcoholic, so it is going to be a dehydrohalogenation. So there is beta and beta carbons here, so there could be a double bond here or a double bond here. So I can have C double bond C, C and C, and also I can have this. This is going to be major product, this is going to be minor product. Here when I see this, okay, alcoholic base, I have my bromine, I want my hydrogen away from me. Here my hydrogen is towards me, both are towards you. I want anti, so I cannot do. Bromine, hydrogen is towards me, this cannot go. This is deuterium, still hydrogen, just an isotope. So this is going to go. Okay, so what you will end up is a double bond here. Okay, and I've just rotated it. Okay, if you want to draw the same way, then I would do this. Okay, this is going to be CH3 here, a double bond here. This and this are same, just drawn differently. Okay, alright. Although if you have got a double bond here, it will be more substituted alkene, but my geometry or the stereochemistry doesn't align, and this bond cannot rotate because it's a cyclic compound, geometrical isomerism. Okay, the next thing we are going to see is Hofmann product, least highly substituted alkene. So when you have a normal elimination, you have Zaitsev product, more substituted alkene. Here you are not going to get more substituted when you use a strong bulky base. Okay, and the bulky base meaning is actually big in size. For example, this is the common bulky base that is given to you guys in NEET. So when you have potassium tertiary butoxide, okay, this one is too big to go and abstract a hydrogen. Okay, that is going to give you the most substituted product. So when you take this example, okay, if you see this, this is more hindered because this carbon is a secondary carbon, this carbon is a primary carbon. So the bulky base can come on this side and abstract this hydrogen more readily than this hydrogen, although both are beta carbons. Because of that, you are more likely to get a double bond here than a double bond here. So anytime you have a bulky base, most commonly potassium tertiary butoxide, okay, when you have this, you're going to get the Hofmann product as the major product and Zaitsev as the minor product. Here's another example. You see that as soon as you see, the way you want to do it in the exam is you don't have to worry about all these mechanisms. Let's say this is given to you. Okay, alright, this is going to be potassium tertiary butoxide. It is going to be elimination reaction. So either I can get a double bond here or a double bond here. These are your thinking. And because this is bulky base, this is more substituted alkene, least substituted. This is going to form, this is going to be minor. Okay, so it's a lot easier this way to think. So Hofmann product is always favored when you have a bulky base because of steric reasons. Alright, so one other thing I want to say is when you do an elimination, it always competes with substitution. When you do a substitution, it always competes with an elimination. So when you have base, okay, if it's an aqueous base, it will more likely undergo substitution. The OH minus will go attack this one and kick out the Br. So you get substituted product. Okay, because this is a secondary carbon, for you guys, it's taken as predominantly SN1. Okay, although it is going to be SN1 and SN2 a combination, this is more likely racemic mixture. Okay, whereas when you take a bulky base, a bulky base for steric reason would love to behave as a base than a nucleophile. Here OH minus behaves as a nucleophile, but if it behaves as a base, purpose of a base is to abstract a hydrogen, not substitute itself. So it will give you a elimination product. Okay, this is where a base and a nucleophile, although it could be the same entity, okay, could be behaving differently. When OCH3 minus behaves as a base, its purpose is to become CH3OH by abstracting a hydrogen. Whereas when OCH3 behaves as a nucleophile, its purpose is to replace a leaving group. This is a concept that you can only master by practice over and over again. Okay. Now here if you see, if I want elimination, the best way to do it is use a bulky base. It always favors elimination versus substitution because of steric reason. A bulky base here doesn't give you SN2 as a major product. Okay. Whereas if I use a non-bulky, I get SN2 as a major product. This you will see that a competition between elimination and substitution decides whether you're going to get an alkene or an ether. This reaction is nothing but your Williamson's ether synthesis. In Williamson's ether synthesis, you cannot choose any base you want. You have to choose the least non-bulky base possible. Otherwise, a side reaction of Williamson's ether synthesis is always elimination reaction. Okay. The next we are going to see is very simple one, dehalogenation of vicinal dihalides. Vicinal dihalides are when you have vicinal or vic means they are present in the vicinity, neighboring carbons, alpha beta carbon or 1,2 carbon, however you want to take, not IUPAC you want to, just neighboring carbons. So this is supposed to be geminal. Geminal means it's on the same carbon. Okay. This is okay. I'll keep the naming separately. Okay. Alkylidene and alkaline, I'll keep the naming separately for you guys. At least know that vicinal means it's on this neighboring carbons, geminal means same carbon. So we are going to look into dehalogenation of vicinal dihalide. When you have vicinal dihalide, zinc with acetic acid will give you the corresponding alkene. You don't have the mechanism. Okay, this goes through a redox reaction. Zinc gets oxidized. Okay, zinc gets oxidized and the carbon gets reduced. Here if you see, the corresponding product is one of the easiest ones. This is actually the level at which it is going to come in NEET. Just put a double bond where it needs to be. That's your product. Okay. So now first we saw synthesis of an alkene from alkynes, two different syntheses, Lindlar and Birch. Next we saw from monohalides, dehydrohalogenation. Now dihalides, vicinal in particular, dehalogenation.